Okay, this is going to be easier compared to the previous part of the course, so you can relax a little bit. Yeah, I will skip the outline and we'll go directly to the subject. So let's start with the old version of C++ pointers. With row pointers, I guess that you know everything already about them. We have basically two different types of usage of this row pointer. The first case is with the memory allocation on the heap. You just make a call to the new operator with a given type T. You can use the pointer, then you have to remember at the end of the usage to delete the pointer itself and release the memory allocation, otherwise you will get a memory leak, of course. The other possibility of the pointer is to have a pointer to an object on the stack, so a local variable. In this case, you just assign the value of the pointer as the address of the variable itself. Other cases are of course instead the usage of the pointer as a pointer to an array instead of a pointer of a single object. The only difference here is that you have to remember to use the square bracket together with the delete, otherwise again you will have a memory leak. So of course this is perfectly fine. We all use them, and I guess that you are using them too. And if you use them inside your code, as long as you remember to delete everything, of course, everything is fine. There is nothing wrong with them. The problem is that maybe sometimes when you start to use them in the API of a library, if you're not developing just your code, but maybe you're developing something, a library, for example, for someone else. In this case, you can find something like this one. This is a function from the GSL library. I don't remember the meaning. I think it's just, multi-fit solver, whatever. So as you can see in the interface of the function, there is a row pointer to this GSL multi-fit f solver type, whatever. Okay, let's say that you are a bit lazy and don't want to have a look to the documentation, or maybe the documentation is missing. And the thing is that if you just look to the interfaces of this function, it's not easy to understand if this object if that particular pointer is a pointer to a single object or maybe a pointer to an array. You don't know if you have to destroy this pointer after the usage, or maybe it's used in other points in your code, so you don't have to delete the pointer itself unless you are sure that everybody has finished to use this pointer in all the places in your code. Assuming that you are in charge for this delete procedure, so that you have to manage this memory release, then you don't know if you have to just make a call to delete the pointer, or maybe there is a special release function that must be used, that is maybe provided by the library itself. Assuming that you need to use the standard delete procedure, you don't know if you have to call delete or delete square bracket, because it depends if this one is an array or a pointer to a single object. And then, of course, you have to consider also all the possible execution path of your code. There can be maybe some exception that is thrown at some point during the execution. You must be sure to include in the delete procedure also that execution path of your code. And finally, you don't know, there is no way with a row pointer in this case to know if the pointer is dangling or not. I mean, if the pointer is still pointing to a valid memory location, or maybe that memory location has been deleted in another point of your code, so the pointer is still holding as a value the address of that particular variable on the heap, but the value stored in that point has no meaning because it has been deleted in another point of the code itself. So let's say that if you're doing everything carefully, this is not a real problem. You can still use the row pointer, of course, but there are some risks, let's say, that are associated with the usage of this object. The idea of C++ smart pointers that have been introduced in C++ 11 is to avoid all these pitfalls of the row pointers, while giving you an interface for the new object that is basically the same of the row one, which is of the old one, which is of course very important, because if you decide to make some work of modernization of your code, you don't want to change everything just because you changed the type of pointer. And the idea is so to give you something that is better in terms of memory management, because they are doing as we will see, everything for you in terms of memory allocation and memory release, but at the same time, they have the same interface of the row pointers. So if you decide to make a work of modernization, you will save a lot of time. You can imagine them as a wrapper around the old row pointer that gives you something more very important in terms of memory management. And they come in 3 different versions. Well, actually, they come with 2 different versions, let's say in terms of ownership semantics. And now I will tell you what I mean with that. But there are 2 pointers type. There are the shared pointer and the weak pointer that implements the so-called shared ownership semantics. And then there is the unique pointer that, as you can guess from the name, is instead implementing the unique ownership semantics. There was another type of smart pointer that was the auto pointer that is now deprecated. It is a leftover from C++ 98, and now it corresponds to the unique pointer. Oh, sorry. We already talked about this RAI idiom. I think that is a good idea to tell you something again about that right now. So the meaning of this acronym is resource allocation, resource acquisition is initialization, which is something that is, every time I don't understand very well. I prefer the other version, which is this scope-bound resource management idiom, which makes much more sense to me. The idea with this idiom is that you have to deal with a given resource in your code. Let's say that is dynamically allocated in memory, for example, which is the case of interest for this presentation. The idea of the idiom is that you can represent that particular resource with a local variable in such a way that when that particular variable is deleted because it goes out of scope, the resource is automatically released for you. And this is exactly the idea, of course, of smart pointers, because the idea is that you want to represent a given resource, and that in that case is a dynamically allocated memory on the heap, with a local variable, which is a smart pointer, in such a way that when that variable goes out of scope, because it is destroyed, of course, for you, the memory is automatically released, so that you don't have to care about that, you don't have to worry about memory leaks. And this local object, this is just terminology, is said to own the resource. And there are different possibilities. It can own the resource in an exclusive way, which is the case of the unique pointer, or in a shared way, that is the case instead of shared pointers. So this smart pointers is not the only example, of course, of this RAI idiom implementation in the C++. There are other cases, like, for example, the containers of the STL. And another interesting example of this implementation of the RAI idiom are instead part of the multi-threading library of the standard C++, and then we will see something about this part in another presentation. So let's start with the shared ownership case and with the shared pointer and weak pointers. So I will start with a very easy example so that you can already understand how they work. So I will start here with the first line with the creation of a new shared pointer. So this is a template class, the shared pointer type. You have to provide the type that the pointer is pointing to. This is exactly what you have to do also for the row pointer. And then here I'm calling the constructor of the shared pointer type, providing a row pointer to a double type, and then also setting the value to 23. As I said, this new object, these new pointers has the same interface of the old row pointer, so you can do exactly the same operation that you can do with a row pointer, like accessing the value and checking, okay, what is the value, that is what I'm doing right here. Then you can make a call to the copy constructor, so that in this case you will have a new shared pointer sp2 that is pointing to the same memory location of sp1. You can create a new default constructed sp3 shared pointer, and you can use the assignment operator here. You can also use the move semantics, as we have seen in the previous presentation. And in this case, you will move the resource ownership of SP1 from SP1 to SP4. You can set the shared pointer to null pointer, as you can do with a row pointer, and you can check the validity of the shared pointer itself exactly as you can do with a row pointer. So as you can see, the interface is quite similar to the row pointers, but then you have something more. And at the end here, I'm creating this new type, this new shared pointer type, which is a weak pointer, and then I will tell you something more about this type in the next slides. And you can create this object starting from a shared pointer. The thing is that with shared pointer, now I come to this point of the execution of my code. The main function finishes, but even if I have a new call, a call to the new operator at the very beginning, so I have a dynamically allocated memory at the very beginning of my code, I have no memory leak at the end of the execution of my code. Because everything in terms of memory management is under control of the shared pointer, so that you don't have to worry about releasing the memory itself. So how do they work? Basically, you can imagine them, well, they are reference counted pointers that can share the same pointed resource, which means that basically they contain, you can imagine them as I tried to sketch here in this small picture. The idea is that when you create a shared pointer, you are creating two objects. You are allocating on the heap two objects. One is the managed resource. This is the real memory, let's say the one that you allocate, making a call to the new operator with the row, like for the row pointer. And then you also make a dynamic allocation of this resource manager object, which is an object that contains two elements, basically. One is a row pointer to the allocated memory. This is a row pointer, an old style pointer, let's say. And then you have two counters. One is for the number of shared pointer that points to that given resource, and the other one is the number of weak pointers that share the same resource. The idea here is that when the number of shared pointer and the number of weak pointer that points to the same resource goes to 0, because the corresponding variable goes out of scope, the memory, the resource manager, and the managed resource is automatically deleted for you from the heap, so that you won't have at the end any memory leak. So you start, for example, with the creation of a new shared pointer. This corresponds to the allocation of two objects, a resource manager and a managed resource. In this case, so you will have the row pointer that points to that managed resource, to the memory allocation on the heap. The number of shared pointer is 1, and the number of weak pointer is 0. Then you start creating in your code new shared pointers and weak pointers with the copy constructor, and with the constructor of the weak pointer that takes in input a shared pointer, so that you are creating all these new pointers that all points to the same memory location on the heap. So of course the counters will be updated, and at the end you will have 3 shared pointers and 2 weak pointers. When the execution of the code goes on, and at some point the shared pointers are destroyed, we will get a number of shared pointers equal to 0, right here. And in this case, when this number of shared pointer goes to 0, the memory location on the heap is released, and correspondingly the pointer, the row pointer inside the resource manager is set to null pointer. But since you still have 2 weak pointers that are still alive, the resource manager is not deleted from the heap. The resource manager is deleted from the heap only when also the number of weak pointers goes to 0, because they go out of scope, and in this case everything will be released for you. So this is more or less the behavior, well, this is exactly the behavior of the memory allocation and memory release with the shared pointers. Okay, let's have a quick look to the basic API of the shared pointers, how we can construct them. This is more or less a complete list. Not everything is here, but these are all the ways you can create this new shared pointer. So you can do that by passing a row pointer. This is the first line of my first example. You can use a copy constructor. There is the move constructor right here. There is a shared pointer constructor that takes in input a weak pointer. you have the assignment operator from a shared pointer, and then you have also the move assign operator. So this is more or less a comprehensive list of the way you can create this a shared pointer. Then you have, of course, some methods in the interface of this object that gives you access to the pointed memory. Otherwise, they will be quite useless, of course. So you have a get method that gives you access to the row pointer. You can access the memory location also with the referencing operators. You can get the number of shared pointer that are sharing the same resource with this use count, and then you have the conversion to bool that is useful for this kind of checks, so that you can check if your shared pointer is a valid pointer or is the equivalent of a null pointer. And then you can change the pointed resource of your shared pointer using the reset method. In this case, it will be set to null pointer, and if it is the only shared pointer alive pointing to a given resource, that resource will be automatically released for you. Or you can, let's say, redirect the shared pointer to a new memory location passing a new row pointer. Talking about a weak pointer constructor and way you can create them, you can see there is a similar list. You have, of course, a copy constructor. You have the constructor of weak pointer taking in input a shared pointer. You have a move constructor starting from C++14. You have the assignment operator. You have the assignment operator starting from a shared pointer. And then you have also the move semantics here implemented for the constructor starting from C++14. Also, in this case, this is, let's say, a comprehensive list of the way you can create a weak pointer. And I have a question here. If you have a look to this list of constructor, and then you think, and then maybe we go back to the list of constructor of shared pointer, you can see that you can construct it starting from a row pointer, starting from a shared pointer, or starting from a weak pointer, basically. If you have a look to this weak pointer constructor list, yeah.
But why the copy constructor of the shared pointer takes a weak pointer?
It's not a copy constructor. It's another constructor that takes in input a weak pointer.
Okay.
The idea here is that if this weak pointer if the weak pointer is valid, which means that the pointed resource is still alive, so there is another shared pointer that is alive, then you will get a valid shared pointer to that particular resource. If the weak pointer is alive, but the pointed resource has been deleted because there is you don't have another shared pointer alive at that point of execution of your code that is pointing to the memory location on the heap, you will get a null pointer for the shared pointer. Yeah, okay, so back to my question. Can you see in the list of weak pointers what is missing in terms of possible ways you can create a new weak pointer? If you compare it to the list of constructor for the shared one. This is just to keep a bit of attention so that you won't fall asleep during the presentation. Okay, the thing is that you don't have any constructor for the weak pointer that takes in input a row pointer, because the only way that you can create a new weak pointer is starting from an existing weak pointer with a copy constructor or from a shared pointer. So this is something we'll come back on this in the next slide. Also, for the weak pointer, you have some methods on the interface, of course, that gives you access somehow, let's say, to the pointed resource. You have to the status of the weak pointer. You have the use count method that tells you the number of shared pointers that are still alive, pointing to that particular memory location. You can check if the weak pointer is expired, which means if the memory location on the heap is still available, has been deleted because you have no shared pointer alive at that moment in the execution of your code. You can get a new shared pointer using this lock method. That, by the way, it will give you a shared pointer, a valid shared pointer to the pointed resource if there is at least another shared pointer to that particular resource. So it means that the memory location on the heap is still alive. Otherwise, you will get a default constructed shared pointer. And then you have also the reset method that sets the weak pointer to null pointer, and then the swap method, which is similar to the reset method for the shared pointer, which means that you can redirect, let's say, the memory location pointed by your weak pointer. Again, I think, yeah, I have another question for you here. Like before, can you see what is missing in this observers and modifiers method in the interface of the weak pointer if you compare it to the shared pointer one? As you can see here, there is no way you can access the memory location directly using a weak pointer. You don't have a dereferencing operator. You cannot do that with a weak pointer, and yeah, the only way you can do that, the only way you can access the memory location, so the value or the object that you've stored in the heap with these smart pointers using a weak pointer, is by creating a new shared pointer using this lock method. So it looks quite strange, because with this weak pointer, basically, you don't have any method to access the pointed resource. The only way that you can create, that you can access that memory location is through the creation of a new shared pointer, and then you can control the lifetime of the managed resource using a weak pointer, because the only way to keep the memory location on the heap is to have at least one shared pointer pointing to that memory location. If you have deleted all the shared pointer to that memory location, the memory location will be deleted. So you will just have the resource manager, but not the resource itself. So it seems to be quite useless, because you cannot access that memory location and you cannot keep that memory location alive. Everything is managed in these terms using the shared pointer. So it seems to be quite strange, but the idea is exactly that one. I mean, the only almost unique usage of the weak pointer is to check if the memory location is alive, the memory location is still there, and in that case, you can access it using a shared pointer. The idea of the weak pointer is having something that tells you if the memory resource is alive without influencing the lifetime of the memory resource itself. If the memory resource is still alive, then you can access it, creating a new shared pointer to that memory resource. And this is quite useful, and I can show you now in a couple of examples. The first one is the one of a circular dependency. Let's suppose that you have these two objects, A and B, and in a data structure, you need to keep a reference from A to B and from B to A. You can do that using a pointer. The thing is that which pointer can we use to make this circular dependency? We can start trying with a raw pointer, with an old-style pointer, let's say, and the problem here is that if at some point in the execution of your code, let's say that the object B is destroyed, then you will have a pointer as a data member of A that will point an object, a memory location that has been deleted. So that pointer will be dangling, and you will not be able to recognize this situation. So that's quite dangerous, of course, because at some point, if you apply the dereferencing operator and try to access that memory location is not containing anymore what you're expecting. So this is, of course, a problem. The second possibility is using a shared pointer. So you will have as a data member of A, a shared pointer to B, and the same in B, you will have a shared pointer pointing to A. And the problem here is that with this circular dependency, you will have at the end, in the execution of your code, a memory leak because of the circular dependency. The destructor of the object will never be called. You can make a test, and you can see that during the execution of your code, when these two objects will be destroyed, they will go out of scope. You can check that the corresponding destructors will never be called. And of course, this will cause a memory leak. The solution to this problem is provided exactly by the weak pointers. And you can imagine now that you can have a data member in A that is a weak pointer to B, and in B a weak pointer to A. And the good thing is that a weak pointer is behaving like a raw pointer in terms of lifetime control of the pointed object, because you cannot keep alive an object just because you have a weak pointer to that particular object. So you're not able to influence the lifetime, and so you won't have the memory leak caused by the missing call to the destructor that you have in the case of the shared pointer usage. But at the same pointer, you can detect if the data member, the weak pointer that is pointing to the other object, is dangling or not, because you can check if that weak pointer is still alive. So the idea in this case is that you have a data member that is a weak pointer that points to the other object. If that object has been deleted, you can check that, you can recognize, let's say, that situation, because the weak pointer provides you some methods to check the validity of the pointer itself. So you can see if the other object is still alive or not. But at the same time, you won't have any memory leak problem, because the weak pointer is not able to keep the other object alive. So the destructor will be called, and you won't have any memory leak issue. I invite you to check everything here with one of the examples that we provide in the repository. Okay, there is another interesting example, I think, that is one of the factory function, and where you can see that weak pointers are quite useful. Let's consider this example where we have a factory function that is used to create this object of type object. Not really original name for my example, and let's assume that this factory function is taking in input, just in this case, one single integer parameter, but it doesn't matter. The thing here is that for the creation of your object, you are doing some very expensive operation, and at the end, after this operation, you will create a new object that will be returned by the function itself. So you have to call this factory function in your code, and you do something like this. You can create, for example, an object obj with for example, this input parameter. At the end of the usage of this object, of course, you will have to delete it. Let's assume, as I said, that here you're doing some very expensive calculation in order computations in general to create this new object. So what if you need to use with an object in different parts of your code? Let's say that you have to call this function for the same input parameter set in different scopes of your code, so that every time you have to wait for all this computational operation to be performed in order to have this object. The idea is that you can save some computational time making use of a caching system, which means that instead using this base factory function, let's say, you can use an updated version where you have an extra, let's say, variable. That is this cache variable here, which is an order map, where the key is the input of the function itself, and the value is the pointer to the created object type. Every time that you try to create a new object for a given input parameter set, the first thing that is done here is an access to the map with this function, with this line. At this point, if the object corresponding to the key, of course, if this object exists, this will be a valid pointer. This obj pointer will be a valid pointer, so you will skip all this part, and the existing pointer will be returned by the function. If instead the access to the cache will give you a null pointer, because the object doesn't exist for that particular key, the pointer here will be a null pointer, so then you will enter the if block. You will get a new object pointer created by the factory function up there. The cache will be updated with the new pointer, and then it will be returned. So this is a way of implementing a caching system in this factory function. The problem here, and this works, but the problem is that then you will have multiple instances of the object pointer for the same input parameter in your codes. This may happen if you're calling this function in different scopes of your code, or maybe multiple times in the same scope. And the problem is that then you don't know when you can delete the object pointer, of course. You can create 10 times the object pointers with the same input, and then at some point you will have to delete the corresponding memory location, which is allocated just one time for you when you update the cache. And the problem is that it can be quite complicated to know how many pointers to the same memory location you have in your code. You need a way to keep a number of these these pointers to the same memory resource. And the weak pointers, well, smart pointers and weak pointers in particular gives you a solution, a very quick and clean solution to this problem. The only thing that you have to do is basically, instead of using a map, a cache that is an ordered map of a row pointer, you can create a cache based on weak pointers. And then instead of returning a row pointer, you will return a shared pointer to object type. So let's see how this works. It's basically identically to the previous example with some steps that are done automatically for you. So let's say that you try to create an object with a given input, integer in input high. The first operation is the access to the cache. If an object, if a weak pointer for that particular input parameter already exists, then this cache element is valid, and the lock function will give you a valid shared pointer. So if the shared pointer is valid, then you will skip all this if block, and the shared pointer will be returned by the function. If instead, for that particular input, you don't have yet a valid weak pointer for that element because it's never been created, then this cache object is a non-valid weak pointer, and this lock pointer will return a default constructed shared pointer, which is a null pointer. You will enter this if block. The weak pointer will be reset from, let's say, from null pointer to a newly created row pointer with this factory function that is the original one. The cache is updated with this new object, and then the new object will be returned. So everything is almost the same as before. We are just using weak and shared pointer instead of row pointer. The good news here is that the external code doesn't have to worry about how many shared pointers and weak pointers pointing to the same resource exist, because everything will be automatically managed for you by the shared pointer themselves and by the weak pointers. So when all the shared pointer will be destroyed in your code, the memory location will be automatically released. And the other thing is also the cache map doesn't need to be updated manually, because here you have a weak pointer, and again the weak pointer, since it's sharing the same resource with all the other shared pointers that have been created, is automatically updated by let's say, by the smart pointers for you. So yeah.
Just about understanding this example. So when I call cached factory locally in a block and then somewhere else,
yeah,
it will recompute or not? Because
no.
The return thing goes out of scope.
Well, it depends. It depends. The thing is that if you're, let's say that you are calling the cached factory, the thing is that you have to, if you call the cached factory with the same input parameter set, the real object creation will be executed only one. The first time you create a new object with that particular input parameter set, in this case is just one integer. Okay, in that case you will have the creation of the object on the heap, the creation of the weak pointer to that particular object, and here also the creation of the shared pointer. Here. You will get a new shared pointer that will be returned. When you make a call to this cached factory function in another point of your code, in another scope, with the same input parameter, the thing is that that part...
Let's assume that the shared pointer I got went out of scope.
Yeah.
In between.
Okay, in that case, if it goes out of scope, the memory on the heap of object type is deleted, because if you just have one shared pointer, when you destroy that only shared pointer, the memory resource is released. You just have the resource manager on the heap, but not the real object. So the thing here is that if you if you make multiple copy of that for that particular input parameter, while the other copy are still alive, you don't have every time to recompute
But
everything.
then I could have used the other copy that is still alive, or not?
It depends on the scope, of course. Yeah, of course, you can pass the same pointer around in your code. It's a possible solution, of course. The idea here is to avoid that,
I see,
to pass around the same pointer around. Okay, just a couple of notes. I have some example where you can just try to use the basic API for smart pointers or make some tests. So I'm just listing here from time to time the corresponding exercise of the current session. So nothing special here. Yeah, as I said, the smart pointers give you the same, let's say, the same interface of the raw pointer, and of course they also have the same features in terms of dynamic polymorphism and casting operation. So this is just a quick example about dynamic polymorphism. There is an exercise about this, so I don't give you the solution here, but it's quite easy, let's say. It's a very basic case. So you have a base class that implements a virtual function f, and then you have the derived class that implements, again, another version, a derived version, let's say, of the same function f. You already know that with the raw pointer, you can do something like this. You can create a pointer to base type with the new operator making a call to the constructor of the derived type. And here, when you make a call to the f function that is provided in the interface of the base function, you are making actually a call to the derived or base class method. Just to be sure that we are all together on this. No, it's dynamic polymorphism. So this is exactly how it works. You have the same method, let's say, in the base class and in the derived one. The base class, the method is virtual. So in this case, since you are creating a pointer to base class, but it corresponds to to this pointer to the derived type, when you make a call to the f function that is present in both classes, you make a call to the derived one. So this behavior, which is called dynamic polymorphism, is available also with the smart pointers, and there is a small exercise that you can try to check that this is true. You have the same features of the raw pointers also in terms of casting operations. So you know that there is 4 different types of casting for pointers. You have the static cast that provides you a compile time conversion check. The dynamic cast that has a runtime conversion check. Then you have the const cast that is just about the constness removal. And then you have the reinterpret cast that has no check at all. This was for the raw pointers. And then you have exactly the same operation, the same casting operation also for the new smart pointers. So again, you have the same features that you have with the old pointers, but with something more in the interface and an automatic memory management. So again, if you're thinking about using them in your code, let's say the modernization work will not be so much because the interface is exactly the same. You have a couple of exercises, as I said, for dynamic polymorphism and casting. But let's move to the last pointer, to the last smart pointer. As I said, there are 2 different ownership semantics that are provided by smart pointers. Shared pointers and weak pointers provides you a shared ownership semantics, which means that you can have more than one shared pointer and more than one weak pointer that points to the same memory resource. And this is a shared ownership semantics. And then you have the exclusive ownership case, which is instead implemented by unique pointers. And this means with unique ownership, I mean that you can have only, at some point during the execution of your code, you can have only one valid unique pointer that is pointing to a given memory resource. You cannot have more than one. And this is, of course, the meaning of unique ownership. So let's have a quick look to the interface of the possible way you can create a new unique pointer. There is a default constructor, which corresponds to the second one, which is set to null pointer. You can create a unique pointer taking in input a row pointer, which is the same that you have for the shared pointer. You have a move constructor. You have a move assignment operator, and again, you can assign it to null pointer. So this is a comprehensive list of ways you can create a unique pointer. And again, like for the other cases, I have a question for you, which is, can you see which constructor is missing here? Yeah, exactly. So the thing is that the unique pointer is a so-called move-only object, as we have seen in the previous presentation. So you can only create it starting from a new row pointer, okay? Or you can only create it starting from a unique pointer, but with a move semantic, so that the old unique pointer will point to null pointer. It will be a null pointer. So the resource. The managed resource, which is the dynamically allocated memory, can be owned only by one unique pointer at a time. If you create a new unique pointer, you want to point to the same memory resource, the old one will have to release the resource. So at any point in your code, you will have only one unique pointer pointing to a given memory location on the heap. Before C++ 17, it was also unique pointer was also a bit different with respect to the shared and weak pointer, not only for the move semantics, but also because it was the only one coming in two forms. A unique pointer to a single type or a unique pointer to an array. Now this is no longer the case because you have also shared pointer that has the same two versions. And the two forms have different specific observers method, which means that for the unique or shared pointer to a single type, you will have the referencing operator, like you have for the row pointer, and for the pointers instead, unique or shared pointer, I forgot to put here the other type, but anyway, also for shared pointer, you will have, if it is a pointer to an array type, you will have the square bracket operator that gives you access like for an array. With an index, you can access the single elements pointed by the pointer itself. And then there are some common elements like the get method that will give you the row pointer, and of course the conversion to bool so that you can check if the pointer is valid. So why do we need a unique pointer? The idea of unique pointer is the one of providing you something that has the same performance and memory, the same properties in terms of performance and memory usage of the row pointer. So you don't have any performance overhead with respect to the row pointers, but at the same time you have this full control on memory deallocation because you're still using the RAI idiom. Of course, you can only use them if you need the unique ownership. But in this case, if you need the unique ownership and you're planning to use a row pointer, you can just use a unique pointer because you don't have any performance overhead, and at the same time, you will have automatic management of the memory allocation and memory release. There is one case in particular where they are quite useful, which is the one of the factory function that we have seen before. In the previous case, we were returning a shared pointer type here. Okay, we were returning a shared pointer type. The thing is that if you do something like this, it works, of course, but you are forcing the user of your cached factory function to use a shared pointer, of course. And this is not always the case. So you can think about updating that factory function using instead a unique pointer. Okay, so that you will give the possibility to the external user to basically to use a unique pointer, which is something that is less flexible with respect to a shared pointer, but it will also use less resources. And in case the external user will need a shared pointer, he can always make a call to the shared pointer constructor that takes in input a unique pointer. So in this case, you will have a more flexible cached factory function for the external user. Well, the external user maybe is the wrong expression, just to say that the user of your library, if you're thinking about developing a library that will include a cached factory function in the API. I have a couple of exercises also for the unique pointers, and then I have a, yeah, sorry.
I'm not quite sure to understand with the cache factory, because if we return a unique pointer, the first time it will work, but then what will we return if we call on the same identifier? I mean, if you call for e equals 0, the second time, what will it return?
The thing is that if externally you're using a unique pointer, it will work like if you're using an arrow pointer, basically. So that's not a problem, but still you will have automatic memory management because of the weak pointer in the cache. If instead you are using...
Yeah, but if I delete the unique pointer, if one of my pointers deleted, it means that all the pointers pointing to this memory are free.
You cannot have more than one of unique pointer to that particular resource. So the thing is that you make a call to cache it to this factory function, and externally you take this output of the function as a unique pointer, so you don't make any kind of conversion. Okay. This is just an example. Then you will use unique pointer. When it will be destroyed, the memory resource will automatically be released for you in that particular case. This is one point. Then if instead you convert it to a shared pointer in your code, then of course it will go back to the previous case. Oh yeah, custom deleters. So by default, this memory location on the heap is deleted by the unique and the shared pointer, making a call to the delete or delete with square bracket, depending on the type. So if you have a shared or unique pointer to a single type, the delete operator will be called. Instead, if you have a pointer to an array, it will be this delete with the square bracket, of course, will be called. But if you have any specific need, you can also provide a specific operation, let's say for the delete procedure, using custom deleters that can be provided as a function or lambda expression, for example, so that during the delete procedure, when the smart pointer will release the memory location on the heap for you, this function will be executed. So if you have any specific operation that you want to complete during this destruction operator, you can do that. You can specify that using these custom deleters. And this is the two cases for a custom deleter with shared and with unique pointer. You can see that this is the custom deleter. That is the second argument of the constructor of the shared of the smart pointer for both cases, for the shared and for the unique pointer type. The only difference here is that the type of the deleter is part of the template parameters in case of the unique pointer. Here you can see that you have the first template parameter that is the type pointed by the smart pointer. This is the same for unique and for the shared pointer, which is the type, the parameter t. But in case of the unique pointer, you have also the second parameter, which is the deleter type. So this means that the deleter is part of the definition of the unique pointer. Every time you create a new unique pointer passing to the template parameter, you are defining a new unique pointer type if the deleter is different and even if the type pointed by the unique pointer is the same. This, of course, has some consequences, and here I have a question for you. So what if I try to create a vector of unique pointers and all the unique pointers are pointing to the same type, let's say double? So unique pointer to double, but they have different deleters. Can I create a vector of a unique pointer with different deleters, but with the same pointed type? The STL is in another presentation, right?
Yes.
Okay, so maybe it's an exercise it's a question for after the STL presentation. So let's keep it there, and then we'll try to answer after the presentation of STL, unless you already have the answer.
Well, I think you can anticipate what the answer will be.
Okay, yeah. No drama. Yeah, the thing is that, of course, if you need to have the vector is templated on the type contained, so you can have only one type inside the vector. This means that you cannot put inside a vector different unique pointers in terms of types, of course, so which means that if you have a set of unique pointers pointing to double, but with different deleters, you cannot put them inside the vector because the deleter is part of the definition of the type of the unique pointer itself. And the second question is instead about this one. This was an old question when the shared pointer type was not available in C++ as a pointer to an array, but I decided to keep it there because I think it is interesting. This is something that you shouldn't avoid, of course, but I still keep it as a question and as an exercise. And the question is, what's wrong with this shared pointer initialization? So I have a shared pointer to double, and I provide to the constructor of the shared pointer a new pointer. This is, this works. The problem here is that I'm creating a shared pointer that points to an array. And again, also this one is left as an exercise. And the question is, what's wrong with this one? So if anybody has an idea right now, otherwise I will go on and then we will try to answer to this question in the exercise.
It will only point to the first element of the array?
Sorry, can you repeat?
It will only point to the first element of the array and then discard the rest?
This was not what I was thinking about, but it's also true. But the thing is that here what happens when this object goes out of scope and the delete procedure is executed. You have to think about what is the standard delete procedure that is executed by a shared pointer when it goes out of scope. And the problem here is that I'm creating this new shared pointer as a pointer to an array. I don't remember. I have to check if I have other slides. Yeah, so. Anyway, I think that we can try to solve this problem in the exercise section. So let's go on. And yeah, I have a couple of information about performances and best practices. So as I said, when you create a shared pointer, you're basically allocating two elements on the heap. One is the real resource, the memory location of type T, where T is a template parameter provided to the shared pointer type. And the other one is the resource manager that contains the counters of shared and weak pointers and the raw pointer to the memory location on the heap. So you're creating two objects on the heap, resource and the manager. This can be, let's say, an issue if you're thinking about performances in memory allocation, but C++ provides you a function, which is this make shared function that takes in input the set of input, a parameter pack that corresponds to the input parameters of the type T of the shared pointed by the shared pointer, is the input parameter of the constructor of this type. And this make shared makes just one single allocation. Instead of allocating two objects on the heap, it makes just one allocation that is big enough to contain the two objects. So basically, you are saving one of the two allocations, just making one bigger allocation, just to save a bit of time. But still, of course, this object has twice the size of a standard raw pointer, of course, because you have let's say the memory location on the heap plus the resource manager. This resource manager that I tried to describe with my, let's say, super easy sketch actually has some complication in terms of virtual function and inheritance. So there is some overhead when the delete procedure starts during the release, during the memory deallocation, but that can generate some overhead in terms of performances. But the thing is that all this virtual machinery is only involved during the release procedure. So unless you are continuously creating and destroying shared pointers, it won't be an issue in terms of performance in your code. There is one critical point for multi-threaded code when you use a shared pointer, because all these the updates in the counters of shared and weak pointers are atomic operation. So if you're creating shared pointers or weak pointers in using different threads in your code, there is a serialization step that is the update of the counters of weak and shared pointers. So it can be an issue for you. It depends on what you are working on. the access of, by dereferencing a shared pointer, the access of the pointed memory location has the same cost of the dereferencing of a raw pointer. Then talking about the comparison between shared pointer and weak pointer, they have the same impact in terms of size and performances in your code because they have the same size in memory and also the same atomic operation in terms of number of weak and number of shared pointers update, so it is exactly the same. The big difference is in terms of performance is with respect to the unique pointer because, as I said, there is no overhead with respect to a raw pointer. So because there is no resource manager allocation and you don't have also this update operation for the counters. So it is just a raw pointer that gives you automatic management of the memory. So if you need just a unique ownership, this is the right choice. This is just a quick summary of everything here. So the idea is, at the end, that of course smart pointers are great if you think about the safe if you think about the safe management of the memory. So they have some overhead in some cases, but if you need the unique ownership, unique pointer is a very good choice because it gives you no overhead with respect to the raw pointer, and then you can use shared and weak pointer if you really need them in the interface of a library, for example. Yeah, nothing special except this first line. Basically, the only other thing that I want to remind you is to never create these new smart pointers using raw pointers, but using existing raw pointers, sorry, but this is something you can see in the exercise. And I think, yeah, the other thing is always use this make shared function. If you need to create a new shared pointer instead of making a call, as I've done in my example, making a call to the constructor of the shared pointer, taking an input, a raw pointer, you can use this make shared function that gives you a single allocation, and it can give you two advantages. One is to have one single allocation instead of having two allocations, and the other one is that if you use this make shared function, you can get rid completely of the old pointer syntax because you don't have to use the new operator, which is something that is inherited from the old raw pointers. Yeah.
Do you suggest to use raw pointers for internal use, or to pass the shared pointer as, let's say, const reference?
Well, the idea here, I think, is that if you are aware of what we are doing, completely aware, raw pointers is still something, of course, that you can use everywhere. I mean, in your code. If you're completely aware and you don't need to do anything special in terms of shared ownership, raw pointer, of course, they are still working and they are perfectly fine. If you need somehow to give as an interface, to provide an interface function with pointers, yes, that could be a possibility, I think. I have to think a little bit about that. Yeah, but probably this is what I will do, is provide the shared pointer, and just to avoid completely the raw pointer in the interface, probably. But I think that Mauro and Anton and Sam as well has much better ideas about that. So.
So I think you should use share pointers are great when you have to reason about ownership, right? Who owns this stuff? There's nothing wrong passing a raw pointer to a function, as long as it's clear that the pointer, you're passing the pointer, but the function will not own the piece of memory, right? So you can pass the raw pointers are actually still probably the best way to pass stuff around. Even better than const ref, yeah, I would say. Yeah. I mean, it's really, you should be aware of the fact that, you know, if you have a unique pointer, you have only one place where someone owns that thing. And every time you pass a pointer around, is not owning the thing, it's just to access the data.
Yeah, I think that was my last slide. So if you have any question.